When I'm looking at fractions, my first step is usually to try to get rid of the fractions by multiplying both sides by the denominator. And that means multiplying both sides by 6 minus x. Well, on the right-hand side, my denominators went away, which is what I was looking for. And on the left-hand side, if I distribute that out, I'm looking at 6x minus x squared. And on the right-hand side, I've still got that x. Now, if you only got one answer, you probably like divided every term by x right now to get rid of the x's, possibly. But you lose an answer when you do that. And I don't want to lose that second answer. So I'm going to move everything to one side, get a 0, and hope it factors. Since I wrote the problem, pretty sure it factors. I'm one of those people that prefers to factor with a positive number in front of my x squared. So I'm going to move everything to the right. And I'm going to make this look like 0 is equal to x squared. And then if I have x minus 6x, I'm going to end up with 5x. Conveniently, I can now factor out an x and have x minus 5, which means I really get two answers. X could be 0 or x could be 5. Today is really going to be all about limits again, is kind of my plan. But if there's anything specific folks want to talk about, for sure you can let me know. We haven't talked about recursive sequences or limits of recursive sequences in here. So I just wanted to do like a couple of quick examples on that. I know that not all of the classes spent much time on this, but some of you did. And for all of you, it's possible that this idea of recursive sequences is going to show up in 17b or 17c. So it's good for everyone to have at least seen it. So we started to think about a problem with giraffes yesterday. And I'm going to return us to our giraffe problem, but I'm going to be strategic about my formula this time. It has nothing to do with reality. I am not a biologist. I'm just making stuff up, but giraffes sound like fun. So, okay. A recursively defined sequence, that word recursive just means that we're going to get an answer, and to sort of go on and move forward in time or move to the next step, I'm going to use the answer that I just got. So as a really simple example of a recursive sequence, I might have something like n sub t plus 1 is equal to 3 times n sub t. Now the notation here with these subscripts, this part over here is kind of like what time it is now. And this over here means the time, oops, one step into the future. Also, just thinking about notation, if I put a little 0 down here, we read that as n naught, like N-A-U-G-H-T, I think, not, n naught, which really just means the population at the beginning of time, whatever that looks like, right? So the beginning of time could be when I started measuring it. The beginning of time could be at the start of an experiment, but that 0 implies the population at the beginning. Are there two N's here, beginning? No, not great at spelling. Someone else, that looks wrong. Whatever, I'm rolling with it. So if I said that in the beginning, my population was 10, then this notation says, if I want to know what my population is at the next time step, I would do 3 times the population right now. In other words, I'd have 3 times 10, and I'd get 30. If I look at the next time step, that would be 3 times the value that we had one time step previous. So that would be 3 times the 30 we just got. And I would be at 90. And we could keep going with this. When we have a recursive sequence like this, sometimes we're able to convert that recursive sequence into some sort of formula where we can just like jump way ahead in the future, right? So in this case, this happens to represent exponential growth because each time the value we have is tripling. Question up front.
So when it says like n to the t plus 1, we now know that the nt on the right side of the equation refers to the one before it, to the answer before it.
Yep, exactly. So this notation just says to get this answer, refer to the answer before it.
What if it said -1 instead?
So I could, the other way that this could show up is maybe this looks like a sub n is equal to 3 times a sub n minus 1. It's the same sort of thing we have here. So this is kind of framed as the time now. And this is the time one step earlier.
So it's just flipped on what side of the equation it's on?
It's not that it's flipped. We still have that the thing on the right is from the previous step. So if I look here, this one is framed as like looking into the future. I'm going to use the answer we just got. This one is framed as looking at right now. I'm going to use the answer we just got. So either way, it's the same thing, that part on the right is coming from the previous step. Yeah. And if you literally thought about steps, it's the difference between like, if this is t and t plus 1 and t minus 1, am I standing here and looking backwards, or am I standing here and looking backwards? But either way, I'm looking one step down from where I'm at. Yeah. Okay. Sometimes when we have these recursive relationships, we can then find like a functional form for that sequence that lets us sort of skip way ahead in the future. So in this case, I mentioned this is exponential growth. And if I was trying to find the pattern here, thinking about the numbers, we started at 10, and that was at t equals 0. At t equals 1, we were at 30. T equals 2, we're at 90. T equals 3, I didn't do that one, but if I did, that would say, take the number we had from 2 and triple it. So that would be 90 times 3, and I would be at 270. So if I were trying to find a different kind of way to write that out, I could say, since I'm tripling each time, I can think about that 30 as really being 10 times 3. And that 90 was 10 times 3 times another 3, or 10 times 3 squared. And that 270 was 10 times 3 times 3 times another 3, or 10 times 3 cubed. So our like shortcut way of writing that would be to say something like n of t is equal to 10 times 3 raised to the t. And that represents an exponential growth equation. It's exponential because, well, this is an exponential. My base is 3, which says I'm tripling each unit of time. And that 10 out in front is telling me what that initial population was. A lot of times, our recursive formulas don't nicely lead to something that we can solve to figure out, like jumping straight into the future. A lot of times our recursive formulas, we really do just have to walk steps out to figure out the next part of the sequence. So I'm going to give us a slightly more complicated one. And my slightly more complicated example here is going to be n sub t plus 1 is equal to n sub t over 6 minus n sub t. Yes. So in this case, if I told us that our initial population here was 4, I want to just go ahead and run this sequence into the future a little bit to see what happens. So if n of 0 is 4, then n of 1 would look like n of 0 over 6 minus n of 0, or 4 over 6 minus 4. I tried to make our numbers nice. What do I get?
Oh, yeah. Yeah.
That's what I got you. So to find my next value, I'm using that 2. So this would look like n sub 1 over 6 minus n sub 1, or 2 over 6 minus 2. Now I'm at 2 over, 1/2, 2 over 4, or 1/2. So n sub 3 would then look like 1/2 over 6 minus 1/2. You could certainly throw something into a calculator. I see fractions. I'm going to multiply by something to get rid of those fractions. If you put this into a calculator, you would get an answer as well, but I'm going to multiply by 2 over 2 so that on top I have 1, and on the bottom, 2 times 6 is 12, and 2 times 1/2 is 1. So I've got 1 over 11. I don't know about you, but I'm not seeing some super easy pattern to pick up on here. But what I do see, let's just go one more step into the future. So I'd have 1 over 11 and 6 minus 1 over 11. What I do see is that these numbers are getting smaller. I'm going to do that same trick, multiply by 11 over 11 to get rid of my fractions. So on top, I've got a 1, and on the bottom, 6 times 11 is 66. And then when I distribute that in here, I'll have a 1, and I'm at 1 over 65. So although I can't really find, I don't personally really see a pattern in those numbers. We could do some work and hopefully find a pattern in those numbers eventually. But what I do see is that those values are getting smaller and smaller. In fact, it looks to me like perhaps the limit of this sequence is headed to 0. But there's a way that we can actually check and find the possible values for the limit of a recursive sequence. To check for the possible values for the limit of a recursive sequence, or sometimes we call those the fixed points, we kind of play this game with ourselves and say, okay, if these really are going towards a limit, then eventually I'm going to get to a number. So let's call the limit L. So eventually, I'm going to be at that limit, and my n sub t is going to be equal to L. Well, the whole idea with a limit is that if I get there, that's where I'm going to stay, because that's the value we were headed towards. So if eventually I get to that limit, then I'm still going to be at that limit one time step into the future. I'm going to be stuck at the limit. which is why sometimes these are called fixed points. And we could also refer to them as equilibria.
So there's no way it'll go past zero and into negative territory, or?
We're going to find out. We're going to now do the algebra to find out. So the good news is we just did this algebra. I just hit it. So if I'm stuck at this limit and I get to this fixed point, then n sub t has to equal to that limit. And in the next time step, I would also be at that limit. So I'm going to take the equation, but I'm going to replace both n sub t plus 1 with L and n sub t. So instead of having n sub t plus 1 equals n sub t over 6 minus n sub t, I'm going to have L is equal to L over 6 minus L. Which should look a lot like our warm-up problem. And we know from our warm-up problem that we got two possible values for L.
So the n sub t or whatever is turned into L for finding the limit?
Right. So both my n sub t and my n sub t plus 1 became L. So if I've actually reached the limit, and so like this is calc for biology and medicine, so let's link this back to some biology. If you've ever heard the phrase carrying capacity, I'm not going to get into like fully what that means, but if we've reached the carrying capacity for a population, that means that based on the dynamics of reproduction for that population, based on environmental factors, right? That's the limit of how many individuals that population can sustain. Well, if I've gotten to that limit and that limit is 5, then next year I should still have 5 in the population. And the year after that, I should still have 5 in the population because I've reached that carrying capacity. Well, this is the algebra equivalent of that, of saying that when I reach that limit, then the n sub t has hit that limit. So next year, that n sub t plus 1 will still be at that same limit.
Because it can't go past.
Right. If I've hit the limit, then I'm not going past that limit. So give me just a second. I'm gonna try to make my case to you even stronger. And one way that I'm gonna make my case even stronger. So there is a question about how we got these. We got these in my algebra warm-up problem. I will flip back to that in a second so you can see. But let's just say that I started with 5 for my population. Then n sub t plus 1, if that's equal to n sub t over 6 minus n sub t, if I started with 5 in my population, then my next time step would look like 5 over 6 minus 5. What do you get for a value?
5.
Which means that next year, I'd be sticking the 5 back in and I'd have 5 over 6 minus 5. Oh, I'm going to get 5 again. I'm stuck. So algebraically, there are values that we're going to get stuck at, that if we ever get close to them, we're stuck there. Same thing for 0, but 0 is usually not biologically interesting. I know it's going to be shocking, but if I have none of an organism, it can't spontaneously replicate from nothing. So we can show, I mean, we can try it, but it's usually not the biologically interesting starting point. However, if all organisms in this population die, they cannot come back from the dead. So algebraically, if we're going to get to the limit, then I know that my n sub t minus 1 would be equal to that limit, and also my n sub t would be equal to the limit. Because it's the place I'm gonna get stuck at.
Okay, so both of them will be equal
Because I'm specifically looking for the place I get stuck at.
Okay, but if they didn't give you that limit, like, cause we have to find the limits, right? We can't- Okay,
Yeah, so I don't know what the limit is. That's why I'm just calling it L. And then we're gonna try to figure out what the limit is. Yeah. So I'm just gonna call that limit L and then try to find it. Well, that means I'm looking at L is equal to the square root of 8 minus L over 3. Do you all want to play with the algebra on your own for a minute, or do you want to watch me play with the algebra? I'm good either way. Yeah, so I'll give you all a minute to try to solve that for L. Personally, would get rid of the fractions by multiplying both sides by 3. That's not the only option. You can drag around that 1/3 with you, but especially if I'm trying to do this like on paper and without a calculator, I'm going to multiply by 3 because I don't want to make a mistake with fractions. So I'm looking at 3L squared is equal to 24 minus L. And if I put everything on the left-hand side, that's like 3L squared plus L minus 24 is equal to 0. How'd I do? Am I matching what you all have? Or I messed up somewhere, so call me out if it's not, if something's wrong. But
I've got the L squared equals 8 minus the L over 3.
yeah, and so at that
Then
point, I multiplied both sides by 3
yeah,
and distributed that 3 through.
I moved the 1/3 L over to the left side before multiplying by 3.
Sure, I think we should still end up in the same place.
Yeah, I still have different numbers. Hold on. I think I know what I did, but
So I don't know if this factors. Oh. So questions coming through in the chat. So I'm gonna go back and do that in slow motion to make sure that I didn't make a mistake on the algebra part.
I don't think
So-
because I realized that I did wrong.
Okay,
Make yours make sense.
so you can shuffle stuff around first or shuffle stuff around later. Either one works. You just want to be careful that when you're multiplying by 3, you're multiplying every term by 3 on both sides of that equal sign. So 3 times L squared gives me 3L squared. 3 times 8, I think it's 24. And 3 times negative 1/3 L gives me just a negative L. Now I'm going to move everything to one side of the equation so that I can use quadratic formula, unless someone sees how this is going to factor. My general rule, by the time you're in calculus, if you don't see how it's going to factor in about 20 or 30 seconds, move on with your life and just use quadratic formula. If it factored, you'll get nice numbers. And if you don't get nice numbers, it didn't factor. Either way, at least you're moving on towards an answer.
Are we gonna be?
We absolutely are, but probably not this quarter.
Oh, so like maybe B or C.
For sure, in 17C, we're going to work with complex numbers. And they might show up in 17B depending on where your 17B instructor goes. Typically in A, we're not going to use imaginary or complex numbers. But if I go ahead and stick this into quadratic formula, I'm going to have L is equal to -1, because I'm taking negative B, plus or minus the square root of B squared, so 1 squared, minus 4 times A times C. Oh, what do you know? We're not going to be imaginary. We are saved by a minus sign. All divided by 2 times A.
Oh, they're gonna be pretty though.
Oh, it's definitely not gonna be pretty. But I've got -1 plus or minus, and in here, minus and minus is gonna make that plus. So I've got 1
It is.
plus, oh, is it? Yep, okay. I was hoping. So can someone, you've got a calculator for me, 4 times 3 times 24, what'd you get?
It's gonna be 280.
288, which when we add 1 becomes a 289, which is the square root, or
17.
which is 17 squared. So gross, but actually not as bad as it looked initially. So -1 plus or minus 17 all over 6. Good times. So if I turn those into actual numbers for us, that means I'm looking at -1 plus 17 all over 6, or -1 minus 17 all over 6. -1 minus 17 is -18, and divided by 6, I'm looking at -3. -1 plus 17 is +16 over 6, and 16 over 6 sounds like they're both divisible by 2, so that's 8/3. If we're just talking about the limiting values of the sequence, and we have been given no context for these numbers, both of these would be fine.
So they'd be, it would have 2 limits.
Yes, and depending on the initial starting value, we're headed to one of those 2 limits.
Oh, wait, so we want it, well, it's squared, so it's not a parabola, so wouldn't it be heading toward the pole, technically?
We're gonna pause that until we're talking about cobwebbing towards the end of the quarter. But if I gave us a starting value and we actually looked at the numbers coming through the sequence, they would either be going to 8/3 or they would be going to -3. But can someone tell me why I know we can't be going to -3 based on the function? Yeah.
We can't have a negative.
I can't have a negative value inside the square root, which actually isn't the problem with the -3, but I can't get a negative value out of the square root. So I could never get to -3 because it could never be the number that popped out of the square root for us.
So that would be the limit?
So it turns out we really do know an 8/3 is the limit.
Oh,